When we did stoichiometry, we worked with reactions that went to completion. So we start out with only reactants, and then all of the reactants are used up to form products, so we end up with only products. Remember this graph from before? The concentration of the reactants goes all the way down to 0, so it shows that the reactants are completely used up, and we're left with only products at the end. But this is only true for one-way reactions, or reactions that only go in the forward direction. Not all reactions only go one way. Some reactions are reversible. This is a reversible reaction. It has a double-sided arrow between the reactants and the products to show that the reaction goes in both directions. So we start out with only reactants, and then some of the reactants are used up to form products, but this time the products will start to convert back into reactants, and eventually will reach a point of equilibrium. That's where the reactants and the products are both present in concentrations that aren't changing, because the rate of the forward reaction and the rate of the reverse reaction are equal. Notice how in our graphs, the concentration of the reactants still decreases, but they don't go all the way down to 0, because again, both the reactants and the products are present at equilibrium, and the rate that both of them are being made is equal. So I'm going to go over 4 conditions for equilibrium. The first condition is that it has to be a closed system, so nothing's added to or taken away from the system once the reaction begins. The second condition is that both reactants and products must be present, but they're not necessarily present in the same amounts. The third condition is that the forward and reverse reaction rates are equal, so the rate that the reactants are converted into products is equal to the rate that the products are converted into reactants. And the fourth condition is constant macroscopic properties, so there's no measurable changes in concentration for the reactants or the products. Now, because the concentration of the reactants and the products remain constant, it may seem like the reaction has stopped. But remember, both the reactants and the products are still being made. They're just being made at the same rate. So the reaction hasn't stopped, it's just at equilibrium. So let's go over a few examples of equilibrium. The first is a saturated solution. When a solution becomes saturated, the rate that the solid solute dissolves into its aqueous ions equals the rate that the aqueous ions crystallize back into solute. If we go through the 4 conditions for equilibrium for this example, it's a closed system because nothing is being added or taken away. Both the reactants and the products are present in the solution, so the solid solute and the aqueous ions are both present. The forward and reverse reaction rates are equal, and the macroscopic properties like concentration or volume remain constant. So if you look at a saturated solution, it may look like nothing is happening, but what's actually happening is the solution is dissolving and crystallizing at the same rate, which means it's at equilibrium. The next example of a system at equilibrium is vapor pressure. A liquid is placed in a vacuum-sealed container where all of the gas particles have been removed. The liquid particles evaporate into gas particles until they fill the empty space of the container, and then they start condensing back into liquid. When the rate of vaporization and the rate of condensation are equal, the system has reached equilibrium. So let's go through the 4 conditions for equilibrium in this example as well. It's a closed system because nothing is being added or taken away. The reactants and products are both present. The forward and reverse reaction rates are equal, and the macroscopic properties such as volume remain constant. When we say a reaction favors the products or lies to the right, what we mean is that at equilibrium, there's more products than reactants. And when we say that a reaction favors the reactants or lies to the left, it means that at equilibrium, there's more reactants than products. So now let's talk about how to graph equilibrium reactions. Remember that at equilibrium, macroscopic properties remain constant, so the concentration of the reactants and products should level out on the graph when the reaction reaches equilibrium. This point is shown on both of these graphs with a pink dotted line. Both graphs start with more reactants, and the concentration of the reactants decreases over time, as the concentration of the products increases over time. The difference is that the graph on the left shows more reactants at equilibrium, and the graph on the right shows more products at equilibrium. So if we're graphing an equilibrium reaction that favors the reactants, or lies to the left, then it should look more like the graph on the left. But if we're graphing an equilibrium reaction that favors the products, or lies to the right, then it should look more like the graph on the right. Now let's make our own equilibrium graph. This problem says to make a graph that shows the reaction favors the products at equilibrium. Use pressure for the concentration of your gases versus time for the axes, and start with 8 atmospheres of NO2 and 0 atmospheres for N2O4. For every 2 NO2 molecules that are used up, 1 N2O4 molecule is produced. So when we draw our curves, we should draw the curve for NO2 going down on the graph twice as fast as N2O4 is going up on the graph, because the rate at which NO2 is consumed is twice as fast as the rate at which N2O4 is produced. When NO2 decreases from 8 to 6 atmospheres, N2O4 increases from 0 to 1 atmosphere. When NO2 decreases from 6 to 4, N2O4 increases from 1 to 2. And when NO2 decreases from 4 to 2, N2O4 increases from 2 to 3. So I'll draw the curve for NO2 decreasing to 2 atmospheres and leveling out at equilibrium. And I'll draw the curve for N2O4 increasing to 3 atmospheres and leveling out at equilibrium. This follows the mole ratio for the reactants and products, but how do we know when the reaction reached equilibrium? Well, the problem says the reaction favors the products, so I just continued the reaction until there were more products than reactants.